Hello everyone. Today we are going to do a very interesting problem in which you need to find the value of critical damping coefficient C. So let's write down this problem. Find the critical damping coefficient C such that the system is given in figure and the mass is also given to you, which is 20 kgs, and you have got a stiffness K of equals to 10,000 Newton per meters, and the system which is given looks like this. It's fixed at both ends and it has got a damping coefficient of C. So there's a damping that is happening here, and then you also have a spring which is basically attached to the system with a single degree of freedom m mass, which is again attached to another spring, and then you have got the fixed end. So the mass will move x deflection. There are two springs, one is of stiffness 2k and the other one is of stiffness k. So we want to find what is the critically damped coefficient Cc in this case. So to do that, we're going to use the energy methods for this. So you know that the kinetic energy and the potential energy equations can be used. But first, the governing equation of motion should be written. So that is equals to the equivalent mass of the system mx double dot plus cx dot plus equivalent stiffness in this case of the system will be equals to 0. Since this is a free system, there is no forcing function that is applied. So yeah, I mean, we need to find the kinetic energy and the potential energy of the system. So the kinetic energy will be equals to half mx dot square, right? So there is only one mass, so this can easily be said as meq, okay? And for the stiffness, you need to use the potential energy equation, which is half K equivalent x square. Okay, so in this case, what is the equivalent stiffness? So if you look at this problem, right, this mass, if this mass deflects by x deflection, okay, let's assume that this mass is moving to the right, okay, then what will happen is the spring on the left hand side will expand and the spring on the right hand side will contract. So the amount of expansion and contraction is going to remain the same. So basically you will have the same deflection, and that kind of means that these are the springs in parallel. Okay, so remember, springs in parallel, they add up the stiffnesses and they have the same deflection. So this looks like to be a system with springs in parallel, and for that the equivalent stiffness will be equals to, in this case, k plus 2k. So that will be equals to 3k. So that is the k equivalent in this case, and c equivalent is basically there's only one damper that is given, so there's only one c, which is c equivalent. So if you put this back into the governing equation of motion, you should get something like this, mx double dot plus cx dot plus k, in this case 3k x is equals to 0. Then you can easily find the natural frequency of the system, which is going to be equals to square root of k by m, and in this case the equivalent k is equals to, so this is equivalent k is equals to 3k, so this is 3k by m. Okay. And the damping ratio zeta is equals to c over cc. Okay, so we want to find cc in this case. Cc is equals to 2m omega n. Alright, so omega n is known, we already calculated that, so that is 2m times 3k by m. Okay, so that's omega n, and eventually you can, so you know what is m, which is equals to 20, right? And then k is equals to 10,000 Newton per meter. So then you will get the cc. Okay, so cc is equals to 1549 Newton second per meter. Please check the calculations, but overall, this is how you can solve this problem using the energy methods. Okay, thank you.